Hello students, so in this session we are going to discuss into more detail about the stress strain and stress strain curve. So first we will discuss about stress strain curve. Stress strain curve. So suppose that there is a body and you are applying some force. The cross section area is A and you plot the graph of stress versus strain graph. So stress is force by area. Remember that this area definitely keep on changing. So we are not measuring it like a instantaneous. So it will be like the area we are not considering changing. Only the external load conditions we are changing. Okay, so definitely the area may be changing. So this is not the true stress strain that we are talking about. This is this will be just theoretically we are taking out. So the in actuality graph may not be exactly the same way, right? So but how it happens, how does the graph look like? Let's understand. So the graph goes like this. You keep on increasing the load force, stress will keep on increasing, and strain will be change of length. Original length is of course L. So change of length by original length. So stress versus strain graph will be first of all a straight line. After that it will be having some curve like this. So this point you can take A, B, and then bottom C it will go, and then after that it may go further and then it may go like this. Here also two important points are there. Okay, so you can take this as C, D, E. These 5 points we can see. Okay, this lowest point we can take. This is it. So this point A is known as proportional limit. Proportional limit. Also we have to know that the elastic behavior is up to point B. Up to point, right? So this point B is also known as elastic limit. Elastic limit, right? And what about the elastic limit? This is also known as yield point. Yield point, because after that plastic behavior starts. Before that is elastic behavior. Elastic behavior. After yield point, plastic behavior. Okay. Now, what about the point C? Point C can be told as the lower yield point. Lower yield point. Point D is the ultimate stress, and point E is called breaking point, breaking stress, or failure point. Okay, so these are some of the important points that we should know. Of course, initially this Hooke's law is valid up to the point A. Up to point A only Hooke's law will be valid, and the slope of the graph tan theta will be the modulus of elasticity, right? Okay, now from this graph already discussed that point A is called the proportional limit. So Hooke's law will be valid up to point A because it's a straight line. But still, body is maintaining elastic behavior from A to B also, but that is a non-linear elastic behavior. Non-linear elastic behavior. That's why Hooke's law can be also further, stress by strain ratio is Young's modulus we say, but in general, or we can say Young's modulus into strain. So, but in general form, stress can be written as Young's modulus into strain power n. So n can be 1, then it's a linear behavior, but n can be other than 1 also. In such case, we can have elastic behavior which is non-linear, right? So n not equal to 1 can be non-linear elastic behavior. Non-linear elastic behavior. And n is equal to 1, like in this case, Hooke's law. Hooke's law deals with linear elastic behaviors. Linear elastic behavior. That's what is Hooke's law. Hooke's law. Right? Okay. After B to C, so at point B, what happens? The body starts yielding. Yielding means plastic deformation starts happening. But from B to C, you can see even though stress or the load is decreasing, there is an increase in the stress or elongation, right? And up to point C, that is, elongation happens. But after point C, there is a very steep increase. So we need to note here that B to C there is not much change, right? In this, not much change in the stress, but there is a change in strain. So this graph, B to C is like there is a lot of change in the stress without much change in the strain. Lot of change. So B to C or BC portion is large strain and negligible stress. Negligible stress. So not much change in stress has happened, but the strain is very large. So this is the fluid behavior. Fluid behavior. Okay. So for example, in fluid, what happens without much stress, there is lot of strain happens. So B to C portion represent behavior of a fluid. After point C onwards, this is increasing continuously. That point D is like the point where we have maximum possible stress. After that, body will be going to break down. Breakdown happens quickly from D to E. So E point is very near to D, right? Also, we need to note one important thing is that material, if you are seeing that, so while it is going to fracture, there will be development of very thin neck, like this kind of structure will be developed because body is going to break at this point. Okay, so here the area will be decreasing and neck formation happens. That will definitely happen so quickly after C. After C, neck formation starts and D to E completely, we are going to separate, and E definitely the bodies will separate into two parts. Okay, this is a very important graph because from this graph we can note important things. One is the fluid behavior, linear elastic behavior, non-linear elastic behavior, and also we can note about the two types of materials which they are going to fail. So one thing we can say about this graph, stress strain graph, if the graph is having more of a straight line and less of a non-linear graph, then this type of material is going to break, fail mostly by more elastic behavior is there. So such kind of materials have more elastic behavior and they quickly fail down like this. So they are like more brittle materials. Brittle materials, this type of graph will be there. So non-linear portion where more plasticity is happening, that is less, and here this is the elastic behavior. Elastic behavior is more. Brittle means generally they are like a very strong materials. Brittle materials are like glass, even diamond also, they are brittle materials. And some of the materials where the elasticity behavior is more, for example, if you see the straight line graph will be less, but more non-linear graph will be there. So such type of materials where there is more non-linear graph, more plastic behavior is there, correct? Less elastic behavior is there. Such type of graphs are having ductile materials. Ductile materials. Ductile materials, generally metals. Metals are ductile in nature. This is one thing that we can note from the graph. Okay, so these things are important, and the slope are more. For example, if you draw the graph, stress strain graph, and if one of the graph is like this, another graph is like this, definitely the slope is larger for this. Let's say this is the first, second. So first has more slope. More slope means more elasticity. More elasticity means more rigidity. More rigidity means more intermolecular forces. Intermolecular forces. You can also say it has more strength. Right? All these things can be concluded based on the shape of the graph. Okay, slope of this graph. So second has less modulus of rigidity, less modulus, less strength, less intermolecular forces, and all that. Okay, so this thing we can make from the graph. Another thing that we should note is, let's note some important parts. That for isotropic materials, isotropic materials means those material which have same properties in all direction. That means their properties does not depend on the direction. Okay, so for such materials we can say that the longitudinal strain, or let's write this as ratios. So longitudinal strain is to shear strain is to bulk strain. This ratio is 1:2:3. Okay, this we should know. Why? Because length means only the x direction, shear means xy, and bulk means xyz, all the three. Okay, so this is just like the alpha, beta, gamma in expansion, right? So this is How all this? Because elongation means the delta L by L. Here shear means that delta X by N, and bulk means delta P by. So they are related if we are going to study their equations, but right now we don't go into more detail about that. Okay, this we should note. Second thing which we can note here, that is about the breaking stress. Breaking stress. Okay, it is the maximum stress that material can withstand without breaking. So definitely this will fall into the region of plastic behavior. Generally, they for consideration of design, they don't consider breaking stress. For design purpose, for design of materials, yield stress is considered. Yield stress is considered as the strength of material. But in many questions they will give you the breaking stress. Breaking stress is like maximum stress that can be applied without breaking. So breaking stress is maximum stress. Breaking stress is the maximum stress. Maximum stress body can be subjected to without failure. So if you want the body not to fail, but of course if you remove that load, body will have some permanent deformation. Definitely this shape and size of the body will change, because this is not the elastic behavior. That is why for design purpose we don't choose the breaking stress as the design stress, we choose yield stress only. Okay, but in most cases we don't care about the permanent deformation that is happening. We simply don't want the body to break. So in such case we can use breaking stress as design criteria. Of course it is not a favorable thing. For engineering purpose we don't use breaking stress for design. Okay, right? But if you have to cut something, if you have to break something, then we have to think of putting stress greater than breaking stress. Yeah, in that case they may be useful. Breaking stress gives the idea of maximum stress where body will not fail. That means you have to go beyond this maximum stress to create a fracture in the body. So this will give us an idea about what stress we should apply to fracture the body. Right? In that case, it is a good idea that we can use breaking stress as a information for that purpose. Right? So to make the body fail, or crack or fracture or break, whatever term you want to use, the stress applied should be greater than or even equal to breaking stress. So in punching or breaking some materials we use this, right, criteria. Okay, next. We should know about elastomers. What are elastomers? Elastomers are substances like rubber. For example, you take rubber. Right? They can be stressed they can have large strain. They can have large strain when stretched. Example is rubber, and the stress strain graph is like this. Stress strain graph is like this. So any objects which are elastomers, they have this type of graph. Okay. And here, although you can understand these are elastic behavior only, but they don't obey the Hooke's law. It does not obey Hooke's law. Why? Because this is non-linear elastic behavior. Non-linear elastic behavior. Okay. And what about the plastic behavior for such substance? So plastic behavior or plastic region is not well defined. Plastic behavior occurs, but the region is not well defined. But the region of plastic behavior is not well defined. Okay. Next thing we should know about elastic after effect. What is elastic after effect? So let's note this: the delay in regaining the original state on removal of the deforming force on a body, that is called elastic after effect. Okay. So what does it mean? That suppose if you apply external force, okay, external force you apply. So what happened? Body undergo deformation. Let us say body has become thin, like this. Now you remove that, so internal forces will be bringing it back to its original position, but immediately it will not happen. There will be some delay. The delay in regaining the original state, right? When you remove that is called elastic after effect. So if you consider a perfectly elastic body, perfectly elastic material, there will be no such elastic after effect. For plastic, for perfectly elastic body, there is no delay, okay, or no elastic after effect. And if you consider the elastic body, so elastic body will never regain, plastic body, perfectly plastic body, it will never be able to regain itself. So the time delay will be infinite. It will never regain that. Right? So elastic after effect will be very, very large for perfectly plastic body. For perfectly plastic body, there is infinite delay or infinite elastic after effect. Elastic after effect. Okay. Next thing that we should understand is elastic fatigue. Elastic fatigue. What is elastic fatigue? Elastic fatigue. Let's understand that the loss of strength, of the material, due to repeated stress on the material is called elastic fatigue. So what happens is that in day-to-day life, the bodies are subjected to not only just stress but repeated stress. This is important to understand. There is a repeated. For example, if there is a chair, right? You are sitting, again, then you are getting up, again you are sitting, again getting up. So every time a body is subjected to repeated stress. This is a very practical thing, right? So how does the body behave again and again, because it is again loaded, unloaded, loaded, unloaded, loaded, unloaded. So there is a continuously, this thing is happening, loading and unloading. So there is a cycle of loading and unloading. Loading and unloading cycle occur. So we have cycle of loading and unloading. The body is being subjected to load, and again load is removed. Again same thing keep on happening. So what happens? The body will lose its elastic behavior, because of this cycle of loading and unloading. So if it is losing this is called elastic fatigue. It's kind of a failure of the body, but it's a different failure. This is happening because of repetition of the stress and strain. Okay. So that's why the bridges or engineering structures, they need to be repaired, because the behavior which we model the material, that we think that the material will behave in a particular manner, it will not behave after prolonged use. For example, a chair, you are using it, and after many years the chair may break down. The material of the chair becomes weaker and weaker. Okay, so that's why material needs to be maintained or replaced. Material need to be replaced or maintained for daily application. Bridges, building structures, many parts of this day-to-day applications, you will see that. Okay, then what is elastic hysteresis? Elastic hysteresis. So what happened, that body behavior changes, and repeated, you are applying loads and unloads. So the behavior does not remain the same. So the strain that is happening in the body tends to lag behind the stress applied. Okay. So in case of rapidly changing, you can write in case of rapidly changing stress, the strain is greater. The strain is greater for the same value of stress in subsequent cycles of loading. Okay, so suppose if your body is getting subjected to lot of stress, again you keep on remove the load, again you start load. That means loading and loading happens. The behavior, they say that the strain is lagging. Okay, the lag of strain behind the stress. This is what is called elastic hysteresis, the lag of strain. So stress strain does not match in the same manner that it should, but strain starts happening more. Okay. So for example, let's try to understand this by a graph. Suppose if you draw the graph of stress versus strain. Let us say the behavior, elastic behavior, initially it is like this. Okay, it is going like this. But now you remove the loading. When you remove the loading, the graph will not come in the same path. It will be coming like this. Right? Now you see here, while you are loading this part of the graph is during loading, and this is unloading. You are removing the stress, or stress is decreasing. So while you were increasing the stress, this graph was going like this way. While you are removing the stress, this graph is coming like this way. Right? So now you can see it is making some area between this. This area represents actually some loss of energy that we will be discussing afterwards. Okay. So there will be some work done in case of stress and in case of strain. So while you are stretching it or loading it, loading means you are stretching it. So while you are stretching it, there will be some work done. So first let's understand what does area under this graph gives. Okay, so we should note that half stress into strain, that gives the elastic strain energy per unit volume. How this formula comes? So just like the spring potential energy formula, which half K x square. Right? Now, if you remember, we can calculate this half K. If you remember, it was AE by L, and this is x square. So here you may also break it into stress into strain. So what is stress? Stress is force by area. Strain is elongation x by L. So let us write this as half K into X can also be written as force here. Okay, you can write it like that, otherwise you can bring it in this form. X can also be written in terms of strain. Let's write X elongation formula, remember, or this elongation X can be written as FL by AY, F square L square by A square E square, FL by AE, right? So from here this AE1 AE will get cancelled here. So this is half into F by A you can take separate, and 1 LL will get cancelled, right? So F L square by E. Okay. So here what we can do is we can try to write, okay, let's write energy by volume, because we need to write energy by volume, that is the energy density. So half K X square, volume is area into length. K now we can substitute, right? So K can be written as AE by N, or Kx can be taken as force, right? Kx can be taken, and x1 x you can separate. So this is what it is, half stress, because force by area, Kx is force is Kx, stress into strain. So half stress into strain, that represent the elastic potential energy per unit volume, or energy density. So if you want to write it potential energy, so half stress into strain into the volume, right? This is the important formula to calculate the energy stored in that material. So here of course volume is same, let us take volume is not changing. So while you are stretching it, you have to do some work, so some energy is getting stored here, and while it is coming out the energy is released. Now we can compare that as the body is you are stretching it, there will be some energy absorbed. Okay, the total energy which is absorbed is proportional to the area of this loop. So what does the area of the loop signifies here? Area of the loop gives us total energy absorbed, in the process of loading and unloading. So in the first process, when you are stretching it, energy is absorbed. During unloading, energy is being released. Now it depends on which area is larger. Like for example, here if you see the upper area is larger than the area under the graph we are talking about. Okay, so for example here stress strain graph, the upper area and lower area, both area you have to compare. So upper area, if you see, this is the upper area, this is the energy absorbed during loading, and if you take, this is the lower area is energy released. So definitely the upper area is larger, so that means energy is absorbed in this process. Absorbed energy is absorbed This is one cycle we are taking, but it can be other way round also. Suppose this graph is like this. It is like this, and while coming it may be like this. That may also happen. So in such case you can see that during loading, arrow direction is giving loading, right? First it is loaded. This area is small, and this time this area is large. This means what will happen? Energy is released. Energy released. Correct? So what will happen? Energy absorbed, energy released. How does it affect the temperature of the body? Okay. So for example, if you see first graph here, energy is absorbed. Energy is absorbed from where? From the same material it is absorbed. So in this case, temperature decreases. Temperature decreases. Energy is released, and that energy will go into the material only. So temperature increases. Temperature increases. Depending on what type of graph it is, we can say about that. Okay, right? Now here we can note some of the important things, because this chapter is theory based, so we need to note all these important things. Springs are made of steel. What is the reason? Springs are made of steel. Made of steel. They can ask what is the reason? Because steel is more elastic. That is the reason. Because steel has more elasticity. More elasticity. Okay. Next thing that we should note is, what about rubber? Rubber. For rubber, elasticity increases with temperature. Elasticity increases with temperature. With temperature, its elasticity increases. These are some of the points which we can note. For involved steel, involved is a kind of steel. Involved steel. Elasticity does not depend on temperature. Elasticity is independent of temperature. That means temperature affects in a different way for different materials. For some materials, elasticity gets increases. Some materials, elasticity has no effect with temperature, right? Now the question is, which is more elastic, rubber, or which is more elastic? Which is more elastic, rubber or steel? Rubber or steel. Now here most of us think that rubber is more elastic, but that's not correct. Okay, the steel has more elastic behavior. Okay, steel has more elasticity. Why? Because it has more intermolecular force. More intermolecular force. Okay, it's very hard, right? Rubber is very soft. Rubber doesn't have that much, because if you apply forces, you can see still you cannot deform so easily. Rubber you can deform easily because it has more plastic behavior. Basically it has elastomer kind of properties, but steel has a very high elasticity because its intermolecular forces are very strong. You cannot easily deform it. We are applying force, but internal forces are balancing, and as soon as you remove it, it is immediately able to come back. Okay. So you can say that when stress for the same stress for same stress strain is smaller in steel than rubber. Okay, suppose if I draw the graph of stress versus strain, right? So same stress by strain ratio you take, that is called Young's modulus. So if it is smaller strain happens, same stress, Young's modulus is larger. So Young's modulus will be larger for steel, and for rubber it may be like this. Okay. So definitely whichever has larger Young's modulus, they have more elasticity. Okay. Then let's go to the next. Okay, so already we know that, and there is one thing called Searle's experiment. Searle's experiment. We don't have to go detail into that, but we should know it is used to find out Young's modulus of a wire. Okay, so suppose some wire is given. How do you find out Young's modulus? So suppose this is a wire. With this wire we can hang, let's say this is fixed here, and you can hang some load, okay, M, some block mass on you. So what will happen to this? And suppose its radius of the wire is r, so area will become pi r square. So the elongation that will happen, x elongation, FL by A, Y or E, you can say Young's modulus. Generally Young's modulus we write by Y, symbol is Y. Okay, because E refers to anything, it can be shear modulus or bulk modulus, but Y is for Young's modulus. Now from here Young's modulus is FL by E into X. Force is here M into G, length is length of this wire, divided by area is pi r square into X. So X will be measured by experiment, right? X will be the elongation that will be measured from experiment. And other things, mass, we will be knowing that, length and other things will know. You can substitute and you can calculate Young's modulus, right? That's what it is. Okay, so any type of questions on this can be solved here. Now let us note next important thing. The next important thing we should note about is like relation between Young's modulus and interatomic force constant. So the interatomic force constant, which is, let us write as K. So this K is equal to Young's modulus into R naught. Here R naught is interatomic distance. For example, suppose there is one atom. Let us say this is one atom, and there is another atom. In between these two atoms, there is an interatomic distance which will be fixed in solids. This interatomic distance is fixed, okay, because solids are closely packed. Now, this Young's modulus is definitely related with the intermolecular forces because it's a modulus of elasticity. It's Young's modulus. Young's modulus. So we can see that and K is what? K is the force constant. What is that force constant? Because it is behaving like a spring ball model. If you think this is like a spring constant or force constant. Okay. So that spring constant or force constant will depend on this Young's modulus. Now how this formula has come, we don't have to go into detail of this. Right, we can right now skip for the main level, it is not required. Okay, but definitely this intermolecular forces depends on Young's modulus, and the spring which is behaving like that, that is spring constant, will depend on this. Okay, then next we should know about how are this modulus of rigidities and other things are related. That's also is important thing. So suppose if you are taking a rod and you are applying a force, so its length is going to change, but diameter also changes. So there is a term called Poisson's ratio. Poisson's ratio. First we should understand Poisson's ratio. So this length is L. So what will happen? Its length is going to increase, L plus delta L, and its diameter is, let's say, D. So this diameter will decrease, D minus delta D. So Poisson's ratio can be written, some symbol we have to give. Let's say this represent Poisson's ratio. So Poisson's ratio is nothing but the lateral displacement, the vertical direction, transverse direction, that strain that has happened. Okay, lateral strain by longitudinal strain. It is the ratio of lateral strain by longitudinal strain. Lateral strain is minus delta D by D, and this is delta L by L. Okay. So this is what it is, Poisson's ratio. Now there are relationships between Young's modulus Y and the shear modulus, which we are saying as G, and the bulk modulus, which we are saying as B, and Poisson's ratio. Okay, what are the relationship between them? What are the relation? Let's write the first relation. So 9 by Young's modulus is equal to 1 by. Now this is 1 by bulk modulus B plus 3 by shear modulus. Okay. Next, second relationship is, or from here also we can calculate the Young's modulus. Young's modulus is 9 times bulk modulus and shear modulus by 3 times bulk modulus plus shear modulus. Okay. Right. G is here, we are taking a shear modulus. This is shear modulus. This is bulk modulus. Bulk modulus. This is Young's modulus. Of course, these are not there in the main question, but in case if it is coming, you can note it. So Young's modulus is 2 times of shear modulus, 1 plus Poisson's ratio. Then third one is Young's modulus can also be written as 3 times of shear modulus, 3 times of bulk modulus, 1 minus 2 times of Poisson's ratio. Poisson ratio can also be written in terms of this 3 times of bulk modulus minus 2 times of shear modulus divided by 6 times of bulk modulus minus plus 2 times of shear modulus. Okay, so all these formulas are there, but generally they are not going to come in the exam. These things are derived from engineering courses. We don't have to go into detail about this. Okay, so that's important thing we have discussed, I think, hopefully everything. And here the diameter can also be written in terms of radius minus delta r by r. Okay, that also we can do. Okay. Also note that the values of Poisson's ratio for some materials, we can note Poisson's ratio. There is a limit for this Poisson's ratio. There is a theoretical limit. Theoretical value is lying between -1 to 0. Okay, so it will be greater than -1 and it will be less than this. Equality can also hold, but the practical limit is from 0.2 to 0.4. Okay, for Poisson's ratio. For incompressible substance, this value for Poisson's ratio becomes 0.5 for incompressible substance. Okay, right, so that thing we can know these values. Yeah. Okay, so I think most of the things we have covered. One more thing that will be coming, so let us take it in the next session. We will complete in the next session the theory part, then afterwards problems. Right. Thank you for your attention.